on here, just going to show you yet another bag of tricks that you can possibly use for solving these, but the first one you should be able to do already with what you know. So go ahead and start doing A. If you need to, look back at your notes from yesterday. Just get your brains warmed up. You just did this a little bit. So we should be ready to go. I'll give you a second to do that. So that was actually the last example from the previous page. That's why I said check your notes if you couldn't do it. But multiplying by the conjugate is a very good technique. Right? If you ever see a 1 minus or a 1 plus something, that means you can do a conjugate with it. And often it will give you something that you can work with. Right? So I show you this now because the next one has something that looks kind of similar. And you want to know the difference of, well, when should I be doing this technique and when not to, right? Because if we just had one technique and it worked on everything, that would be great, but unfortunately we're not as lucky, right? So, but of course we could multiply this together, and because it gives us a squared here, that's what makes it so valuable. So you have to look at what will it give you, what would it yield in order for you, to use it, should you use it or not. So the fact that we can go from having cosines to cosine squared, which 1 minus cosine squared equals sine squared, is what makes it worthwhile doing it in the first place. Now on the next one, if we tried the same thing, I'm not going to put it through it, but if we tried the same thing here, you'll notice how there's a 2x here. Having the 2x there kind of changes things. It doesn't give us this nice simple answer where I can get sine squared and whatnot, right? So this formula, this formula right here does not work very well if we have like 2x's and 2 thetas and things like that. So instead, we use a little bit of substitution. Now, if we're going to substitute for sine 2 theta, well, there's only one possibility. That's this one, right? Because you'll notice we have one formula for sine 2 theta, but we have 3 formulas here for cosine 2 theta, or 2x, or whatever variable it is, right? But one of them stands out because it deals with sine and strictly only with sine, and that would be this one. So my advice to you is that if you have a cosine 2 theta, or a cosine 2x, that you start with this one because it gives you this sine squared theta, which works really nice in these problems. Whereas over here you end up with a sine squared, but you also have a cosine to deal with, so it could make things more difficult by introducing that. Same thing over here. This gives us a cosine only, which could be nice because when we're taking a limit as it goes to 0, that might be the better way to go. It just depends on the problem. So in other words, on some of these you just have to try, right? See if it works. If not, try the other one and see if that works, right? And chances are one or more might work. There's different ways of doing these, so you might find a different correct answer. Okay. So for this one, let's try the one I pointed out. Let's substitute in 1 minus 2 sine squared theta. And I'll get to that in a moment. Yeah. So let's do that. So this part right here, all right, I'm going to do a direct substitution. So I'm just going to turn it off. So I'm going to have my limit. And I do need to keep writing this part until I actually take the limit. So keep writing that part. All right. And then I have what cosine 2x is equivalent to by the theorem, 1 minus 2 sine squared of x. Okay. And we can clean this up a little bit by distributing the negative. So we'll just have 2 sine squared of x over x squared. Of course, bring down that limit. And based upon what we did yesterday, hopefully we're starting to get a better eye for it. If not, just keep looking. But you're trying to look for, like if I have something like this, sine squared, you want to pair that with an x squared, and that's what we have right here. So it's good practice to write these separately. And say, well, this is 2 times, and I'm going to rewrite this in a certain way for good reason. So I don't know if you remember this, but sine squared of x is the same as this, sine x squared, with parentheses. Okay? And little side note, sine squared of x equals quantity of sine squared. However, it does not equal sine of x squared. So this is one of those things that the parentheses definitely makes a difference. So look how close this is. Quantity of sine squared and sine of x squared. So if we take the sine of a number and then square it, it's not the same as squaring the number and then finding the sine. Because these are so close to each other, that's why these two, we write it this way, so that we don't accidentally, mix these up, because it's so close. If we didn't have this way of writing the squared on the sine, we'd have to constantly put parentheses around every single thing that's sine, just to avoid the confusion. So it's good to know that, because for simplification purposes, it's really useful right here, right now. Okay. Another side note, that if you had something like this, like that, 4 squared over 3 squared, that is the same as 4 over 3 quantity squared. And that's what we're going to end up doing here. Because I can't really say, well, am I using this theorem right here? Does that work that way? Because it worked when it was like 2 theta over 2 theta, but it doesn't say anything about these being squared, right? So what we could do is just algebraically change this just ever so much and say, well, this is the same as 2 times, and then I'm going to use this. Instead of having squared over squared, I'm just going to write in parentheses with one thing squared, right? So this whole thing squared. And yes, I should technically have the limits. I haven't done that yet, so it should be there for both of these. Squeeze it in. And this is exactly what our formula above says, right? It does equal 1. So I can take the limit, and what's going to happen, I'm going to get 1, but it's going to be 1 squared, which is 1. So when I finally take the limit here, right, it's going to be 2 times 1. You get 1 for this whole thing, squared, but just equals 2. There we go. All right, so go ahead and do number 1. Very much the same, and I'll just tell you up front, use the exact same substitution. So for this cosine 2 theta, use this as well. Use the 1 minus. And it's going to simplify in a very similar fashion as this one. Just look at both sides as you're doing it and kind of match it as you go down. I'll give you a second to do that. You can check with each other. Now, as you're doing these, be very careful with your thetas, because thetas have a way of turning into zeros, which can have like a line going that way. So just be very cautious when you're doing theta that you're doing a horizontal line through there. 1. Time. Okay. So that's simplified, and we got just negative 2 sine of squared theta. Okay. And we do have just like a 2 over 2 right here. So we could cancel those out. That's okay. And left with that negative. That's right there. And then we have something very similar to what we just did on the other side. So if we want to, I can kind of combine these. And then when we take the limit, we'll end up with 1, which is squared, of course, just equals 1. And I should have, all the way up to that last step, I should have the limit as theta goes to 0 at each step until I actually do the limit. It needs to be there. And then right here, when I actually do it, it will be fine. Okay, so not too bad. And oh, don't forget, I forgot my negative. That negative, negative, okay, negative 1. Now, the last one won't take too long. It's a takeoff of what we did yesterday over here. So you saw the problem from yesterday where you multiplied top and bottom like by 6 over 6 to get like a sine of 6 theta over 6 theta, right? Or the next problem after that, I think we multiplied by 4/3 over 4/3. Well, we can do the same thing but with thetas and with x's, right? So on this one, you know that we have sine theta, and we need sine theta over theta. So in order to get this theta underneath, I can just go through and just divide everything by theta, right? It's just a very convenient, very small thing that can actually solve a lot of problems. So I'm going to rewrite this and just leave a lot of room right there, because I'm going to write something underneath each of these terms. Okay. So what I'm doing, I'm going through and I'm just dividing every single term by theta. Like so. Okay. Technically what I'm doing is I'm multiplying everything by 1 over theta. So dividing by theta is the same as multiplying by 1 over theta. So however you want to think about it, the important part is that you do it to all the terms, right? So this is the technical step that we just did, right? But in effect, it makes everything look like, oh, it's over theta, over theta, over theta. And then, of course, we're still just taking the limit here, right? Let's go to 0. So we know that this right here, sine theta over theta, that equals 1. Right? We know sine theta over theta, that equals 1. And then last on here we have theta, 2 theta over theta. Theta cancel, just like an x would cancel. So it's just plus 2. So my final answer just turns into 1/3. So nice little trick if you could recognize it. Like, would you be better off just dividing everything by a single number or variable or angle theta? And if that gives you, what you're looking for, then perfect. Okay. All right. So that's it. Let me pass out the homework.